Hey everybody, so I am going to lecture you through some stress and strain. We obviously already had a YouTube video doing some explanation of that, but I want to just do some exploration with that so you understand it a little better. That's what your homework that I created that is due tomorrow on Wednesday, that's what that was for. And I'll probably, for the most part, I'm going to flip this to screen record and you'll just hear my voice. And see the whiteboard, quote whiteboard that I create for you. I may go back to some video as well of me during some explanation points. Hopefully this is helpful, and feel free to send me a text if you're struggling with something and we can try to connect. Thanks. Talk to you soon. So today we are going to be talking about stress and strain and understanding what essentially is very introductory materials or mechanics of materials. All right, so I went and pulled this image up, so let's start with this. And this is something that you will have thought about before and not really realized that you thought about it. So this curve, we're gonna make sense of this curve during the course of this discussion, okay? So right now this doesn't mean much to you, but I'm going to help it make sense. Okay, let's switch to red here. So first of all, along the bottom here of this curve, or graph I should say, is strain. Now we'll define strain in a second. But let's also point out that up here is stress, and it's marked right there, right? And so as we get higher up here, we're starting at 0 stress and 0 strain. And as we get higher on this line, we're going to maximum stress up here. And as we go further to the right, we're talking about higher strain way out further, okay? So let's define what stress and strain are. Set that aside for a second. Consider a spoon, or let's consider a slinky. You guys have all played with a slinky. I've certainly enjoyed slinkies, okay? So here's a slinky. It's not in its tightest capacity right now, right? Because of course, a slinky just sitting there is essentially very tight, kind of like that, right? And when you pull it out with your hand, right, you move it this way a little bit and you hold this hand still, or I like to draw that with a series of cross-hatched lines, the kind of fixture. When we do that, right, you get even spaces coming between them. When you let go with your hand, it springs back and recollapses, right? Now, you know, if you let your little brother or little sister mess around with the slinky, they are not so careful with it. And sometimes you wind up, when you let go of it, instead of this picture here, right, you wind up with a slinky that looks like this when it collapses. Now, obviously, very imperfect art, but the point of what I'm making is, all of a sudden, you wind up with some portion of the slinky that will no longer collapse, right? Now, when we talk about strain, there's two kinds, okay? So let's talk about the first kind, what we call elastic strain, okay? So elastic strain is strain that will reverse itself when the load that's applied, so you apply a load and something stretches, say from here to here, and when you let the load go, it springs back, okay? So strain is basically defined as the ratio. So strain is defined as the ratio between the deformed shape. So I'm going to say the length deformed over the length relaxed, okay? And so this would be the relaxed state of the slinky, right? this would be the deformed state of the slinky. This would be a slinky with a combination of being in a relaxed state, right here and here, right, and a permanently deformed relaxed state. And we call that a different kind of strain. So remember, like I said, this is elastic strain. This one here is picturing plastic strain. And the reason we call it that is that the material is getting kind of malleable and squishy, like imagine warm plastic or something, versus something made out of metal that springs right back. Okay, so metals have a plastic range and an elastic range. All right, and what happened to the slinky here is that little sister or brother pulled so hard from this point here, let me switch colors so it's easier to tell, from this point here and this point here, that the slinky was strained beyond the elastic region and into the plastic region. Okay, so let's go look at that curve again and understand that better. So imagine that slinky. When we start with the slinky, it's at 0 stress, so there's no force being applied to it. And it's at 0 strain, so that's right here, right? When we start pulling on the slinky, two things happen. One, the metal in the slinky is starting to resist some amount of force. Oops, let's undo that. Some amount of force. And like we've talked about before, force through an area of material is what we call stress. Hopefully I've defined that. If I haven't, I apologize. Maybe let's split off for 1 second real quick and make sure that stress is also clear. So we've just defined strain in this section here. Strain. Now let's define stress and make sure that that is clear as well. So stress is when you have a material, and I'm going to be real simple here, it's a little bar, right? And that bar is held tight on one side and pulled from the other side, okay? Now let's just imagine, for the sake of argument, that across the area, if I cut this like a stick of butter, then that little circle that would be left on both sides, let's imagine that it is 1 square inch, okay? And if I looked at it from the end, it would look like that, and it's 1 inch square total area, right? Now, I'm pulling on it with a force. Let's imagine that that force is equal to 100 pounds. Now, stress, oftentimes indicated by this, what we call sigma. Sigma, it's the Greek letter sigma. Stress is defined as a force over an area. So in the case of what we have here, we'd have 100 pounds over 1 inch squared, or 100 psi, which is short for pounds per square inch. All right. So that's the definition of stress. Stress is a measurement of how much a material is having to resist being torn apart or squished together, right? So remember we talked about there's two kinds. If it's being torn apart, it's tensile stress. And if it's being pushed together, it is compressive stress. Compression. Okay? Or compressive stress. So let's do this real quick. Let's put tension or tensile stress. Okay. So, stress, check, we've defined it. Strain, check, we've defined it. Let's go back to our graph. Let's see how far into this little shenanigans I am. Never started my timer. Sorry about that. Okay. Zooming back in on our stress and strain curve. So we talked about the slinky starting right at the bottom left-hand corner here, right? It's at 0 stress and 0 strain. We start pulling on it, and now there is deformation of the slinky, so we're moving along the right-hand side of this. But we're not staying on the bottom line here, because the bottom line would suggest 0 stress, because our stress goes up as we move vertically on this graph, right? And we know it takes some force. Now, slinky is pretty soft, so it doesn't take a lot of force, but there's a little bit of force going into our slinky. And so that means we're also creeping up this graph this way, okay? And all materials are like this. But metals have some special properties. And one of those properties is that within a certain range, and it's up to what they're calling the proportional limit here, within this range here of stress, when you let go, the material will snap all the way back down to the 0 point at the bottom left-hand side. There will be no permanent deformation of the object. So, if you pull your slinky out, and in this case, let's use our graph here. So let's say we pull our slinky out from right here, and we're pulling it along, and we stop pulling it right here, okay? If we stop pulling it right here, when we let go, it will spring back all the way. And the path that the dot travels, or the graph of the stress and the strain, the path that it will travel is basically along this line, okay? So here we are. We pull on the slinky, and then we let go, and it springs back down to that 0 point again, okay? Now, let's suppose we pull on the slinky a little bit harder. Okay, we pull on the slinky, it gets all the way to this point here. Okay, that's still going to be okay. It's going to spring back all the way to the 0 point here. No permanent deformation, no plastic strain. All right. Now let's pull farther. Okay, we start on here, we're pulling along, and this is little brother or little sister this time, and they keep pulling, and if you graphed the amount of force that you're putting in, which is directly related to the stress, right? We've talked about that. So if you graphed it relative to how far the stretch has occurred, it's no longer going to be in a straight line. You notice if it was still in a straight line, we'd be running up this here, but it's not anymore. It begins to bend or deform faster than it was before, and the load, the stress, does not go up as fast, okay? And so the angle of this graph is changing. It's turning over. Now, guess what happens? Let's say we get all the way here to this point here, and we let go, okay? This is what the metal does. It does not follow back down the same path that it took to get there. Instead, it springs at the same angle as the original stress-strain line that's along this path here, okay? All the way back down to 0. See this distance right here? That's the slinky having plastic strain, okay? That's the distance right here that we just talked about on the graph, okay? So the slinky has permanently deformed now, okay? And we can do this further. Let's erase this line again. And we pull this further. Now, the specifics of this graph vary from even from specific steel to other specific steel, vary from aluminum to steel, vary between copper and aluminum, etc. So this graph here is generally representative, but it might be a little bit different for different materials. For aluminum, this straight part is flatter, okay? But it still has a yield point, and it still goes up afterward, and then eventually, we haven't gotten to that part, breaks. Okay, so I'm going to erase that for now, because we're going to stick to ours for now. So if you pull the slinky even further, okay, there's even more of this damage being done, okay? And you can let go. It still hasn't broken. The slinky is still not broken, and when you let it go, it will still spring back. All the elastic part will spring back at that same elastic direction, okay? But you'll notice what's happening to your slinky. The gap in your slinky, the permanent gap in your slinky, oh, come now. Let's stop moving that. Okay, move back to pencil. We are. Sorry about that. Okay, the gap in your slinky has now grown tremendously, right? So whereas maybe before it was a small gap in your slinky, the gap is huge. There's a large amount of what kind? Plastic, remember? Strain that has occurred right here. And this distance along the bottom of the graph from right here, that's a measure of how much plastic strain has occurred. The amount of movement back, so if you look at this material here, right, when you let go, it goes from here to here. Do you see that movement back? That's how far back it jumps. That's the elastic portion of the strain. Okay. Elastic. Okay, that's the elastic portion of the strain. The rest, right down here, is plastic. Okay, let's look at another example. Let's take a paperclip. So the paperclip looks like this. Oh boy, doesn't look like that. Sorry. Okay, paperclip looks something like this, right? And the interesting thing is, we can take this paperclip, right? And we could bend it a little bit over, and then let it go, and it could spring back with basically zero change, right? So what we've done is we have kept it in the linear elastic range, or it has experienced elastic strain. If I move to pushing this further, right? I bend it over, and now I let it go, and it got all the way to here, let's say, but when I let it back over, it only springs back to this point here. Now I have a combination of, right, in here is the elastic portion, and then up here, I'm going to erase my last line. Up here is a plastic strain region, right? I have permanently moved the material. Okay, I'm going to pause right here, make sure this recording is working, and then we'll get started again. Okay, good news, intrepid physical scientists, aka class. Looks like the video is working okay. I did notice that when I move around, I make a bunch of noise on the microphones. I'll try to keep that to a minimum. Apologies for that. And now we'll get back to it. We've covered the elastic range of the material. And then we covered the plastic range. And so our handy dandy graph is actually labeling the plastic region, right? with all blue. All the blue stuff is all considered plastic region, okay? And the elastic region is our green region right here. Now, let's continue following, because so far all we've done is, as we have continued to pull on the material, the slinky, the paperclip, whatever it is, as we have pulled on it, the force has gotten higher. So here's where we stopped, right? And the force, every single time we pulled, it continued to get higher. At some point, that stops being true, okay? And we call that the ultimate strength of the material, okay? Now, some materials will break. As soon as they get to their ultimate strength, they will just fracture, okay? And you could think of glass being an example of that. In fact, glass has very little plastic region. It pretty much goes straight from its elastic region into fracturing, okay? Metal has a much larger plastic region. And when you hit the ultimate strength, a lot of materials will continue to strain, will continue to move to the right on this graph, but something fundamentally different is happening. The load required to move the material goes down. So it actually gets easier as I continue pulling on it. It's easier to get it to move, okay? And it takes less force and less force and less force. And then at some point, it just detaches and the force required drops all the way down to zero because the two pieces have broken, okay? So let's sort of trace out a graph like that. All right, so we're creating our own graph like that, and we're going to take that paperclip. So we yank on the paperclip, and it doesn't move very far, and we let it go, and it jumps back, right? We've established we're still in the elastic region, okay? Pretty quickly, though, it reaches a point where when I let it go, let's redraw that. When I let it go, it will not spring back to the same location. It will have some plastic strain, right? All right, we keep pulling it and the load continues to go up. Eventually, we reach a point where I can keep pulling it, but it actually gets easier to move it, okay? And every time I go slow, it wants to turn it into a straight line. Okay, and then eventually it breaks, right? Ultimate strength. Okay, and this is our maximum load here, right? Because remember, this was stress, this side of the graph. So that's as much load as we can put through, right here, as much load as we can put through our material, okay? But remember, our paperclip is dramatically deformed anytime we're in this region here, right? Because when we let it go, let's say we let go right there, boom, we spring back down here. The paperclip has strained a long way, right? So if we were to label in this graph the elastic region, and then the plastic region, that's how we'd label it, okay? The plastic region is typically defined as 0.2% strain. Because in reality, when you zoom in up on this really close, this is not a sharp transition when you get right up on this point right here. Okay, it's not like the material goes dead straight and then boom, hits an angle and starts to angle over. Now it's when you zoom up on it, so if we zoomed up on that, like so, in reality it looks more like it's coming up, and then it just starts to move over a little bit more. So there's no really clearly defined moment when you can say, now it's happening. And so what they do is they define if this little distance here of tip from the perfect straight line that you were on before to the new permanent deformation that would occur, if that exceeds 0.2% of the length, then we call that plastic strain. And if it's less than that, we say, yeah, you're still basically in the elastic region, okay? So let's be aware that that's a bit of a fine point, but nonetheless, that's what's happening. Okay, let's think about a couple materials. Let's take a piece of glass, okay? So if I was holding a piece of glass in my hand, and I drew a stress strain curve for glass, okay? As I bent it, it would not bend very much. The load would go up very quickly, and then it would just stop. What happens when I stop? Well, it breaks in two pieces, right? Essentially, the glass always stays in its elastic region, and the second it gets to plastic stress, it just shatters, okay? So this is what we call a brittle material. Brittle, okay? And the stress strain curve, remember stress is up here, remember, and strain is down here. Strain is also sometimes epsilon is the Greek letter used to represent that, okay? So here we have a very brittle material. Okay, let's pick another material. Let's pick clay. Well, let's not pick clay. Let's pick rubber or something. It might look something like this. It might do this. There's no region where you get a nice straight line for some significant distance where you could say, here's the elastic region of the material. It has no elastic region, okay? So that would be something like rubber, some plastics, etc. And you would probably find clay would similarly pretty much deform permanently as you put load onto it. Very, very little elastic region, okay? Steel, we kind of already drew a picture of. Steel, or let's do another color, sorry. So steel would have this nice, steel would have this nice straight region, and then it would start to bend over and go for a while and eventually break right there, okay? So that would be kind of what steel might look like. And you might find some steels that can get a lot, that can get a lot higher than this, so they can run on the linear region where they're not permanently bent a lot further before they start to yield over. And some steels, very, very hard ones, might go just a little ways and then break. That'd be a very hard, brittle steel, okay? On the other end, you might have a relatively soft steel that could only go up here and then would start to bend over. Okay, they're going to have the longest region that they will tolerate straining, but they're just not as strong. They never resist as much load. So steel can vary. I'm going to give you some numbers here. Steel, the sort of super average, generally weak steel that you might just use if you went down to Home Depot and bought a piece of rebar or angle iron, might be 36,000 pounds per square inch, which, remember, we call PSI. Now that means that's the yield strength. Yield, okay? So that might be this one right here is at 36, okay? On the upper end of steel, which would be tool steel, very hard steel, might have a yield strength of 200,000 pounds per inch squared, or PSI. And that's, again, a yield strength. Okay, think about how much further that is on the graph. I've not exaggerated this enough. And ultimately, if 36 was at this line here, 200 is way somewhere up here, which is kind of crazy. So steel varies in strength dramatically, and it really depends on the alloying of the steel, the little bits of other materials you put in, like vanadium and nickel and moly, chromium. There's a bunch of different metals that you can alloy into the steel, and they all have different effects in terms of how hard you can get the steel to be and how much strain it has, how brittle it is, etc. And so we use different steels for different things. You can imagine that this steel here, with a long plastic strain region, is pretty helpful with just kind of steel that needs to be able to be pounded around and shaped into something, steel that doesn't have to be particularly strong, etc. Steel that needs to be able to tolerate being bent without breaking. Steel that you want to be able to, say, pound into a specific shape, things like that. You're going to want a weaker steel, actually. Still lots of strength, 36,000 pounds per square inch. So if you had a 1-inch bar, this big around, you could carry 36,000 pounds through that piece of steel. That's a lot of weight, right? Okay. On the other end of the spectrum, you might have something that you don't care if it's brittle. That's okay. But it needs to be really hard. You do not want it to change shape when it gets pressed on by something very hard. And so then you might use a tool steel. And there are many steels in between. Steels that are stainless, right? They don't corrode very easily. Steels that maybe go up to 100,000 psi yield strength, or 80,000. Most structural steel is around 50,000 pounds per square inch. So a large range of different materials. And again, what I want you guys to learn and understand here is the relationship between strain and stress, right? And how that varies between materials, and how there is a region of the of steels especially, and metals in general, that is elastic. It's like a rubber band. It will spring and spring back, spring out, spring back, right? And won't be bent permanently. And then gets into this next region, this plastic region. And I gave you a little bit of homework to help you think about that and work through that. I'm going to go take a quick peek and make sure I've taught everything that will help you with that homework, and then we'll come back and close this up. Let's say I have a bar of steel here, okay? And if I set that bar up on blocks, so I have a block on this end and I have a block on this end, okay? And then I support a weight from this thing. So I tie a rope around it, okay? And it goes all the way down here, and I hang a big weight on this. And I am heavy weight. Okay? So, when I do that, think about the stress-strain curve that we just talked about. Okay? You know that when I put a load onto steel, it will move, right, in proportion to the weight that is applied to it. Okay? So let's think about, in your mind, intuitively, if you did this with a stick, whatever, you've done this in your life, you know intuitively that the deformed shape of the beam might be something like that, right? It's going to bend down, isn't it? Now let's think about what's happening to the material of the beam when we do that, okay? So the beam has taken on this new smiley shape. So I'm going to draw it in kind of permanent marker now. Okay, so my piece of material has taken on a smile, hasn't it? And my weight, of course, that means my weight has moved down a little bit, doesn't it? Okay, now if I stayed in the elastic region of the material, if I took the weight off, the beam would spring back up to its original position, right? When it didn't have weight on it, sort of straight across. Let's imagine for now, we're leaving the weight on there. And in fact, why don't we we can erase the rest of it so that our diagram isn't confusing. All right. So there we go. That's a little less confusing. So our beam has taken on this deformed shape. Now let's think about what's happening to the beam. On the bottom, if I were to measure out the distance from the end of my beam right here to the end of my beam right here, I would actually find that the distance had gotten longer from here to here than in the unstressed beam. And on the top, all the little parts are actually getting squished together. So the distance that I'd measure from here along the top, let's change colors to make that clear, along the top right here, that distance has gone down a little bit. So the top of the beam is being squished. And you might remember I told you that was called compression or compressive stress. Okay? And the bottom of the beam has the opposite happening to it. It's being stretched. Let's do it outside of the beam. So it's being pulled like that. Okay? And it's getting longer. And so it has tensile stress. Okay? Now, that's what's happening on the beam. Where do you suppose the bending is the worst? Where is it the highest on the beam? I'll give you a second to think about that. You might say it's the same all the way across. That's actually a really reasonable guess. Turns out it's not quite accurate, though. The bending stress is going to be the worst. So if we drew like a little graph of what the bending stress was like below this, the bending stress is the smallest at the edge, goes up, 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 and it reaches a peak at the middle and then comes down, 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 like so. Okay? So that's the bending stress. Now we know that it's tensile on the bottom of the beam. It's compressive on the top, okay? There's another thing happening here, and that is that the beam, in the middle, the beam is being stretched apart, like it wants to be pulled in pieces, right? But when you get to the edge of the beam, I just have a bunch of load that's pushing downward right here, right? And I have the beam being pushed up on by the block right here. And the result of that is that's not a tensile stress. It's not a compressive stress. It's what we call a shear stress, okay? It's when you take a material and you're trying to shove the top one way and the bottom the other way. And the material is going to take on a parallelogram shape, so to speak, as you deform it, okay? That's called shear, okay? So the beam sees a bunch of shear right at the corner, okay? And that shear drops down and down. And you might guess, and you'd be right if you did. Let's do a little erase first, though. Oh, maybe not, actually. Let's keep that. Let's just switch colors here. So if I said, where is the shear stress the highest? If you guessed the outside, you'd be right. Boom, boom, boom. It's highest here. And if you guessed where it's lowest, you'd be right to guess it's in the middle. Okay? So this is the shear stress. Shear stress. Okay. This is why, if you ever look at a beam that might be in construction, you might see like floor joists, for example, might be like this, and they might be cut with notches at the ends of the beams, okay? The reason is when you get at the edge to the edge, and let's say it's supported here by a wall or something, when you get to the edge, shear through this area right here is dominating whether or not that beam is going to be okay. Okay. Turns out you might not need as much beam depth for the shear as you need to resist the bending. So you have a deeper beam out in the middle where you need all the bending resistance, because remember the bending is maximum here. By the time you get to the edges, the bending stress is basically gone, right? Because remember, it's at a maximum out in the middle here, and then it's going down to 0 at the corners, right? So if I filled that in, there's our bending. And now the shear is coming up to a maximum, and the shear gets to go through this whole area. Shear doesn't necessarily need as much depth as the beam would need to resist bending. Now you can imagine that has a lot to do with the geometry of how you set this up. So if I took a beam and put a huge load on it, but I put my supports very close together, right? So here's my support 1, support 2, okay, and I put a beam on this, and I put a huge load right here. I don't have a big space for the beam to turn into a smile, right? I have a very short distance, but my shear is very large going through this section. Maybe my shear resistance of my beam becomes the thing that dominates, not the bending stress. Now take the same depth beam, but put the supports very far apart. Okay, all the way out there, same depth, okay? And I put the same force here. Well, it turns out you couldn't support that same force. You'd break your beam because it's going to bend too much like that. And the shear is exactly the same if this was the same load, isn't it? And if you, like I told you, well, you can't support that load, so now you reduce how much force you're putting in. So now this is a much smaller arrow, and we're going to erase this. Why did I do that? Okay, so now we have to put a smaller force here. It's not as big, okay? And so the shear going through our section at the corners, just not as high. And we can tolerate a notch, should we need one, for the geometry of our build, okay? So we just identified where shear is the largest and where the compressive stress is the largest, where the tensile stress is the largest, and gave you a little bit of an understanding of what shear is, right, versus what tension is, right? If I drew that same thing over here with tension, I'm doing this and it's just getting longer, right? So it's turning into a longer piece, right? And if I'm in compression, I'm doing the same thing, but I'm pushing in, right? And it's getting shorter. Okay, that's all the principles I wanted to share with you for. Okay, great. The video looks like it's worked well. The homework tonight I've already sent out to you. You did the first part for today. You can turn that in to Jen before you leave. And then the second part is in that same PDF towards the end, and it's just helping you wrestle a little bit or think through again the concepts from this. And you can do that for tomorrow, for Wednesday's class. Thanks so much. Be ready to turn that in, and I'll have one more video for Wednesday.